this method to a more generic case. But let's test with the goals. So the goals are two. The first one will be achieved more or less at half of this talk. And as you will see in a few seconds, the main point for the BV construction is the introduction of these ghost fields. So the first goal is to understand what is the geometric meaning of these ghost fields. For the second goal, you should wait really until the end of the talk. And I will explain you how this BV construction can be seen within non-commutative geometry. So, but more precisely, so at the beginning, I will give you the picture of this BV approach with some flavor of the physical motivation. And then I will introduce this, the mathematical notion to describe this construction, which is this BV variety. And then it will enter the game, the main chapter. This is our U2 matrix model. And for this model, I will show you what is the BV variety. And then we will talk about this BRST cohomology. And for this cohomology, we will see that it's possible to be related to a generalized notion of Lie algebra cohomology, which helps to detect some further structure. And finally, we will go back to non-commutative geometry and introduce this BV-spectraltriple. So this is the way in which we formulate this BV construction in the setting of non-commutative geometry. But let's start with the physical flavor. So this is the context in which the BV formalism appear, and it appears with the quantization of a field theory. So when we try to quantize a field theory with the path integral approach, we have the problem of solving this kind of integral, where x0 is the configuration space, s0 is the action, and g is a regular function over the configuration space. So more or less on the right, we have our theory, and on the left, we have this expectation value of the function. So we have some computable stuff. So the point, so the problem is that when we consider an action as 0, which is gauge-invariant, then there are local invariants. And are these invariants that doesn't allow to quantize straightforwardly the theory. But this problem has already been solved for a while ago by Fabian and Popov, and they suggested to introduce these ghost fields. So the idea is to introduce extra fields in order to eliminate these symmetries. And they are called ghost fields because they are definitely not physical. And so these ghost fields were first introduced like a tool in order to solve this kind of computation, but then they turn out to be more interesting. So what was discovered is that they are generators for a cohomology complex that is known under the name of BRST cohomology complex. So our goal is to understand the geometrical meaning of these ghost fields. So the starting point is a gauge theory. So for me, a gauge theory is simply given by a pair, x0, s0, where x0 is the configuration space, while s0 is the action functional that is defined over the configuration space with real value and is invariant in the action of a gauge group. So given this initial theory, what we want to do is then enlarge it with these ghost fields. So what is the idea? The idea is to construct another pair, which is this extended pair given by this x tilde and then an s tilde. So about the x tilde, this will be of this form. So it's given by the sum of two pieces. So in this is a z-graded vector space. And in degree 0, we have our initial configuration space. Then we have a positively graded part that is the one containing all the ghost fields. And then for the negatively graded part, this is just, let's say, the symmetric with respect to the positive side. So the idea is that physically, to each field and ghost fields, we should correspond an anti-field and an anti-ghost field. So this is the reason for which we have this structure. So once is known the not negatively graded part, is also known the negatively graded part. And moreover, x tilde is supposed to be endowed with this anti-bracket structure. What about s tilde? So for x tilde, we are so it's supposed to be a regular function over the full extended configuration space, given by the sum of our initial action plus terms involving the ghost fields and the anti-ghost fields. Moreover, we require that this satisfies the classical master equation. This means that this equation is equal to 0. Perfect. So once we have so this is more or less the idea. This has been formalized in the notion of a BV variety. This has been done by Felder and Karzan, and they did also something more. So they proved that this BV variety actually exists under some hypothesis on this base space. So the idea is that we have an initial base space that is this variety M. So this is supposed to be a non-singular algebraic variety. Then the configuration space is just the vector space generated by the coordinates over the algebraic variety. And then under this hypothesis, they prove that it always exists a BV variety associated to the initial theorem. And the proof is constructive, so they explain to you how to construct a possible X tilde. So the way to obtain this X tilde is through a Tate resolution of the Jacobian ideal defined by the initial action over the structure sheaf of the variety. For what concerns S tilde, this is obtained via an algorithm. The important part is that here I'm speaking about a possible BV variety, but everything is well defined in the sense that this is unique up to gauge invariance. So from a physical point of view, we are safe. So let's look to our, this is the point of introducing our model. So our model is a matrix model coming from a finite dimensional spectral triple. So there is really a deep connection between spectral triples and gauge theory. So each time we have a spectral triple, this naturally gives rise to gauge theory. But in our case, we can just consider finite dimensional. This is the case that we are interested in. And everybody knows all the conditions about a spectral triple. But let's say that in the finite case, this is definitely easier. Because when we are considering a finite dimensional spectral triple, the Hilbert space is just finite dimensional. For the algebra, this is a unital star algebra that is faithfully represented over age. But in the finite dimensional case, this means simply that A is just the direct sum of matrix algebras. And D is a self-adjoint operator. So given this structure, we can construct a gauge theory in this way. So again, a gauge theory is just given by an initial configuration space, an action, and a gauge group. And for the configuration space, this is given by the inner fluctuations, namely this symmetric one form inside omega 1. And so these are simply linear combination of elements of the algebra together with this commutator of the Dirac operator with, again, an element of the algebra. And among all this linear combination, we selected one that are symmetric under the star operation in the algebra. So this is our configuration space. And the action is simply the spectral action, so which is given by the trace of f of d plus phi. And the fact that we are in a finite dimensional case implies that here f is simply a polynomial. So the last ingredient is the gauge group that is given just by the unitary elements of the algebra. Yeah, so it's really a finite dimensional case, so we are dealing with matrices. So yeah, so but let's say that, yeah, we are just, that is the case that we are going to analyze, yeah. So but the fact that we are in a finite dimensional case means that we are always playing safe, more or less. Yeah. So because this is exactly what we are going to consider. So we are going to consider this finite dimensional spectral triple where the Hilbert space is given by Cn, and the algebra is really easy. So we are only considering n by n matrices. And of course, D is a self-adjoint n by n matrix. So let's apply the construction that we have seen before in this case. So what is the corresponding gauge theory? The corresponding gauge theory is just a UN matrix model where the initial configuration space is given by the self-adjoint n by n matrices, and as 0, as I said, is the spectral action, which is invariant and the joint action of the unitary element of the algebra, and in this case it's simply UN. So this is our UN matrix model, but actually for now we are just going to consider n equal to 2 and to apply the construction for this particular case. So for n equal to 2, this is our situation. So as I said, the configuration space are just self-adjoint 2 by 2 matrices, but since we're going to do some explicit computation, let's just identify the space with R4, just picking a base. And M1, M2, M3, M4 will be the coordinates over this space. For what, so in this particular case, we are fixing the real basis given by the Pauli matrices. So for what concerns the action, it can be proved that should be of this particular form. And so the fact that M4 is playing a different role is due to the fact that this is the coordinate corresponding to the identity in the base. So what we want to do now is to construct the extended pair. So this is the extended theory. Remember that X tilde was supposed to be of this form. So recalling the theorem, what we have to do is to apply the Tate resolution to the Jacobian ideal that is nothing more than the ideal generated by the partial derivative of the action as 0. So this Tate resolution should be taken over the ring of polynomials of our initial fields MA. And here we have a condition more. So from where this is coming, so it's coming from the fact that with the Tate resolution, what we are determining is just this part. So namely, we are determining the negatively graded part in the, for this X tilde. So we are determining this part. So more or less, we are detecting what are the anti-fields and the anti-ghost fields in this construction. But we know already something. So we know that we are starting with these fields here. And as I say to you, so to each fields and ghost field should correspond an anti-fields and anti-ghost fields. So the first thing is to introduce the anti-fields corresponding to this one. So this is the reason for which this first step in the resolution is already fixed. It's determined by the fact that we have to introduce the anti-fields corresponding to our initial fields. So the freedom is starting only from degree -2. So I'm not going to explain you all how to make explicit the Tate resolution, but what I want to explain and is give you the idea of what these ghost fields are telling to us. So I want to convince you that there is a connection between the number of ghost fields that need to be introduced and the symmetries of the action as 0. So let's take our action once again. And so you can immediately notice that if I take a transformation that is sending the variable M1 in the variable M2 and then M2 in M1, this is of course a symmetry of the action. And something completely analogous can be done for M2 in M3 and M3 in M2, and again, sending M1 in M3 and M3 in M2. So these are all symmetries, independent symmetries among pairs of variable in the action. If we want to be a little bit more precise, we can say that the number of anti-ghosts of degree -2, which need to be introduced, is related to the number of independent linear relations among the partial derivative of S0, so which are exactly these relations. So then we have to introduce 3 anti-ghosts, C1 star, C2 star, and C3 star, and the color here are matching with the color there. And these anti-ghosts have degree -2 and parity 0. So this means that these are real variables. But of course, this is not the only possibility, so there is another one. We can, of course, send M1 in M2, M2 in M3, and then M3 in M1. And this is, of course, again, a symmetry of our action. But let's say a more complicated one. So because it's involving all the 3 variables at once. And for this reason, we have to introduce another anti-ghost field, so that is this E star. And again, a little bit more precisely, we can say that the number of anti-ghosts of degree -3 is related to the number of independent relations existing between triples. So this time we have to consider triples of the partial derivative of the action as 0. So then we have to introduce this only one anti-ghost of degree -3, and this time the parity is 1. So this is a Grassmannian variable. So to conclude, this is the full picture. So our configuration space is given by, so we start with our initial fields in degree 0. So then this was fixed because we have to introduce the corresponding anti-fields. And here is what we have just determined right now. So for the positively graded part, we have just to double this part. And so the color are just telling to you that these are all real, while these are all Grassmannian. And as you can see, the parity of a field is the opposite with respect to the parity of the corresponding anti-field. So this is concerning the extended configuration space, and this is the extended action. So this is just obtained through an algorithm, but what I would like to underline this point is that this extended action is linear in the anti-fields and quadratic in the fields. And this will be important in the following construction. So now that we have, so let's just make a small remark about the physical properties. So we can say in some sense that the two physical properties that distinguish Gauss fields, that are namely their Gauss degree and the parity, are related to the Tate resolution. So in some sense, they have, say, a geometric interpretation, in the sense that the Gauss degree is exactly representing the degree of the step in the Tate resolution in which the Gauss has been introduced, and the same is for the parity. So a small summary. So we started with a spectral triple. We constructed the induced gauge theory, and then we used this BV construction to obtain from this initial gauge theory this extended pair. So what can be the next step? So the next step is to proceed with this gauge fixing procedure. So the point is that physically we don't want to have any anti-fields or anti-Gauss fields. But we cannot just remove them brutally, but what we have to do is to introduce this gauge fixing fermion. So this gauge fixing fermion is a polynomial depending only on the fields or on the Gauss fields, and should have total degree -1 and parity that is a Grassmannian parity. So let's say that up to now, we are not able to construct this gauge fixing fermion in our model, because for now we have only not negatively graded fields. So then what usually is done at this step is just to enlarge a little bit more the extended configuration space, adding these trivial pairs that are not changing anything from what would be then the cohomological point of view, but are just helping to really introduce this gauge fixing fermion. But so let's assume that we have enlarged a little bit more our extended configuration space, and we are able to define this gauge fixing fermion. Once that this is done, we can proceed with this gauge fixing procedure, and that is acting like this. So given our extended theory for the configuration space, we don't have to do nothing, and so in the sense that we are just forgetting all the anti-fields and the anti-Gauss fields. While for the extended action, we have to impose this gauge fixing condition. So each anti-fields or anti-Gauss fields will be substituted by the partial derivative of this gauge fixing fermion taken with respect to the corresponding field or Gauss field. So the important part is that also after having done this, carry out this procedure of the gauge fixing, the action is still satisfying this equation. So this means that the action is invariant under the BRST transformation. So each time we have this kind of equation, we can define a cohomology, a corresponding cohomology. And this is what we are going to do now, and this is the BRST cohomology complex. So for what concerns the space of the cochain, so the cochain of degree k are simply the given by the degree, the part of degree k of this graded algebra, which means that we are considering symmetric polynomials of degree k with coefficient, the polynomial of the initial fields, and in these two variables. So remember that Ci were of degree 1, Grassmannian, and E is a real variable of degree 2. So for what concerns the coboundary operator, this is just can be seen as a graded derivation that acting like this over the generator. So what we did was to compute this BRST cohomology group for our U2 matrix model. And this is what we get. So look into what happened in degree 0. You might recognize something here. So this is exactly the same formula that we had for the action. This is, of course, linked to the fact that H0 is describing all the polynomials in the initial field, this M1, M2, M3, and M4, which are gauge-invariant. And this, of course, was the way in which we characterized zeros as a gauge-invariant function in the initial field. Then here you can notice that there is a periodicity, and this is due to the fact that we have only one generator of degree 2. So in odd degree is not happening anything, so it's always trivial, and also here is more or less trivial. So something interesting is happening in degree 2. So, but now let's just look to this BRST cohomology from a slightly different point of view, because we can make this remark. So if we fix the Gauss degree and consider the dual space defined by this Gauss field, this can be endowed with a Lie algebra structure. So more explicitly, if we take C1, C2, and C3, and then we consider the dual of this space, this is just a Lie algebra that is just a SU2. For what concerns E, the dual of this space is just U1. So each time we have a Lie algebra and a module over it, there is a notion of cohomology that is this Lie algebra cohomology. So now a natural question is, can we find any relation between our BRST cohomology and some suitable notion of Lie algebra cohomology complex? So the answer is yes, but we need to do something before. So, but let's start by recalling what is the actual definition of a Lie algebra complex. So each time we have a Lie algebra G and then a module over G, we can define this complex where the space of the cochain is given by, so the cochain of degree k are just the k linear alternating map defined over G with value in the module. For what concerns the coboundary operator, this is of degree 1 and is given by this expression. So mainly there are these two sums. In the first one is playing a role the module structure. So this here is entering the module structure, while in the second one there is the Lie algebra structure that is appearing here. So this is the usual notion, but we have to generalize it a little bit in two directions. First of all, we need to be able to consider symmetric map instead of only alternative map. And moreover, we need more freedom here, so in the module. So we will introduce the notion of a module of order P. So let's start with this, this part. So this definition is not so complicated. It's just giving us a little bit more freedom here. So a module of order P is just given by a pair, where the first term is just a collection of vector spaces. So, and for the second pair, this is just a collection of linear maps defined like this. So once we have this structure, we can consider the first generalization, let's say, so the one that is considering symmetric maps. So once we have this G module and this compatibility condition among these linear maps, then we can define this symmetric cochain complex. As I promised, here the cochain are given by symmetric maps. And of course, so here we are considering symmetric map defined over G with value in this Vi, and then of course we take the sum, the direct sum of all the possible target spaces. For the coboundary operator, this is composed only from, let's say, the first term, in the sense that here is entering this generalized module structure, but we don't have anything involving some Lie algebra structure, because of course here we are dealing with symmetric map. So there would not be possibility to make any Lie algebra structure entry in this case. So we have here only the module structure. So this is the first direction in which we want to generalize this Lie algebra complex, and the second one is this one. So one, we want to consider again these alternating maps, but with some more freedom in the module. there are something that, I mean, it's getting a little bit more involved, but this is what we get. So for what concerns for what concerns the cochain, here we have again alternating map, but with the freedom for the target space. And then, of course, we have to take the direct sum over all the possibilities for it. In this case, for the coboundary operator, we still have both the possibilities. So here is entering the model structure, and once again, we can take in account also the Lie algebra structure on G. So now that we have all the structures, so why we are doing this? So the point is that we can identify already at the level of complex, our BRST complex with this expression. So the reason for which we want to have more freedom in the model structure was exactly to be able to take complex over complex. So in this case, this module of order 1 is coming from this cohomology complex. So I want to underline that here we have the two possibilities. So this is the symmetric Lie algebra cohomology, so the first generalization, and this is the other one. So here we are considering alternating map, while here we have symmetric map. And this is really telling us something about the ghost. Why? Because remember that G was generated by the dual of C1, C2, and C3, which were our Grassmannian fields, our Grassmannian ghost fields. Therefore, when we consider the dual, we are dealing with alternating maps. And for this reason, we have to consider this kind of cohomology. Here, we are considering the symmetric version of the cohomology because this is age that is just defined by the dual of E, which was a real variable. So this construction is really detecting the difference between the ghost fields. So here is entering, let's say, the parity of the ghost, while here is entering the ghost degree. Why? Because we have a different weight for these two indices. So the fact that here it appears a 2 is due to the fact that E has a ghost degree 2. Yeah. So, and this is already visible at the level of cochain, but also, of course, at the level of the coboundary operator. And this is the coboundary operator of the symmetric Lie algebra, while here is the other one coming from the alternating part. And so with this approach, we are able to detect a double complex structure. So it's, let's say, a shifted double complex structure. And here, the color is the same, because when we want to consider the BRST complex of degree, in this case, 2k plus 2, we have to take these two pieces together, and of course these other two together. So as I said, this is a double complex precisely, so then of course the operator here, coboundary as operator, and for what concerns the squares, they are anti-commuting, and this is appearing here a minus sign. Of course, so this map is injective, but the interesting part is that if we take the diagonals, so here with a term more, so this full sequence with 4 terms, so this is exact sequence. So we had already found this relation at the level of cochains between the BRST and this generalized notion of Lie algebra, but what happened at the level of cohomology groups? So this is what we had. So in degree 0, we don't see anything more than G, of course, so just for a matter of grading. So the situation in degree 1 is still a little bit confused, but let's say that from starting with degree 2 and so on, it's really clear what is happening. So each cohomology group in the BRST setting can be seen as this direct sum. So what I would like to remark is that this is not coming just from the situation, but any double complex satisfying the previous properties is such that when we consider the total complex, this can be written as the sum of these complexes coming from, these cohomology groups coming from the subcomplexes. So it's a more general situation. But so a few remarks. So the point is that with this kind of approach, the BRST cohomology, so what was not so clear, the level of the BRST cohomology, because all the ghosts were all considered all together. So it's more clear with this point of view, in the sense that it's really distinguished what is happening. So what are the contribution of the different kind of ghosts? So now we achieved the first goal. So let's go for the second. And so now we want to. As I said, our model was constructed by a spectral triple. So we started with a spectral triple. We defined the initial gauge theory. We applied this BV construction. So now our goal is to formulate this BV construction in terms of non-commutative geometry. So the idea is to construct a new spectral triple to describe this extended pair. And the idea is that the action will be appearing as the fermionic action of the new spectral triple. So given a spectral triple, in fact, we have two notions of action. So given a spectral triple might be real. So of course, we have the spectral action, that is what we have already used. But we have also the notion of a fermionic action. That is something like this, where J can appear here. And this is defined for psi that is inside a certain subspace of the Hilbert space H. And of course, this subspace is also part of the definition of the fermionic action itself. So why this can be the right way to go? Because often the fermionic action is involving Grams-Mannian variables. And these are exactly what we have. And so that was the right way to go. So this is what we found out. So this is what we will call this the BV-spectral triple. And so from our extended theory, we got information to construct the Hilbert space, the operator, and we are forced to introduce a real structure. What I want to tell you immediately is that from our extended theory, we didn't have any condition on the algebra. So the extended theory is telling only something about the Hilbert space, the operator, and the fact that we need a real structure. So let's look a little bit closely the Hilbert space. So this is given by the sum of two terms. So about the first one, this Hm, this is just a copy of M to C, and it describes the fields MA and E. The second term is again a copy of M to C, but this time this is describing the fields Ci. And for what concerns the real structure, it's just sending a vector in I times is adjoint. So for the first term Hm, this is, as I said, M to C, and this can be split as sum of these two parts. And this is what we will call HMF. As I said, this is describing the field MA and E in this sense, in the sense that a vector inside this space has as components these fields, M1, M2, M3, and E. For HC, this can again be split in this way, and this is what we will call HCF, where the components are C1, C2, C3, and C4. You might remember that there was no C4 before, so, but this is not a problem. So you will see that for the form that it will have the Dirac operator, C4 will never play any role. So we can say that it decouples. It's not a problem. So the important part is that is this one. So that the fields that we have, so this MA, CI, and E, are the components of the vector in this subspace of the Hilbert space. So the fields are in the Hilbert space. What about the Dirac operator? So this is the Dirac operator, and as you can see, this is a 8 by 8 matrix, and this block is pretty different from the others. So this is what we will call D2. This piece, and the other pieces are more similar, but in any case, these two, so the off-diagonal one, are depending on this anti-field M star, while this diagonal block is depending on C star. So this is why we are considering the operator as given by these three pieces. So the one in the corner, and then the two off diagonal and diagonal. As I said, the algebra is not playing an important role. So for, this is M to C, and the way in which you decide to take M2C is just because this is the largest algebra for which the first order condition is satisfied. So, but the important part here is that the anti-fields are appearing are entries of the operator. So, once that we have the Dirac operator, we can consider the corresponding fermionic action that is of this form. So what we can prove is that when we consider this part as a 3 linear pairings with respect to the first entries, the second entries, and the Dirac operator, this is gauge invariant under the adjoint action of the unitary element of the algebra. But since in this case this is just M2C, the unitary is just U2. Perfect, but there is a problem. So this pairing can be seen as given by these two pieces. So a part that is depending on D1 and a part depending on D2. What is possible to consider so is that D1 is anti-commuting with the real structure, while D2 is commuting with the real structure. So this implies that when we consider the pairing coming from D1, this is an antisymmetric bilinear form, while the contribution of D2 is given by a symmetric bilinear form. Then, if we want to have a not trivial contribution coming from D1, of course, we have to introduce Grassmannian variables. So the point is that we cannot do this brutally, just saying, okay, all the vectors C are Grassmannian, because otherwise we will not have any contribution from D2. So the point is to say that some of the components of C are Grassmannian, but also some of the entries of the operator are given by Grassmannian variables. And this is the solution. So the components M1, M2, M3, and E of the vectors in HMF, and also C1 star, C2 star, and C3 star that were appearing in D1 diagonal and also in D2 should be real variables. While C1, C2, C3, and C4, which were components of in HCF, and also M1 star, M2 star, and M3 star, which were inside D1 of diagonal, should be Grassmannian. So this is the only possibility in order to have really a not trivial contribution coming from both of these parts. And this is exactly what we had from our model. So to conclude, so this is, as I said, the algebra is not playing a role. It's just the largest one for which the first order condition is satisfied. And as you immediately notice, so D1 and D2 are playing different roles. And if we consider the triple defined with a Dirac operator given only by D2, and remember that was a 4x4 matrix, so that was acting only over HM, this is a real spectral triple of KO dimension 7. So, but let's look this a little bit closely. So remember, so in HM we had the fields M1, M2, M3, and E, while inside D2 there were these anti-gauss fields. So in some sense, this is the bosonic part. So both for the Hilbert space and also in the Dirac operator are just appearing the bosonic fields. So and what about, so yeah, that's the bosonic part. What about if we consider D1? So remember that D1 was again an 8x8 matrix. So this time we have to consider the full Hilbert space. So if we consider the triple with the Dirac operator given by D1, this is the real spectral triple of KO dimension 1. And this is in some sense describing the fermionic part. Why? Because so in D1 of diagonal were appearing these antifields, which are fermionic. In HC were appearing these Gauss fields that were fermionic. In D1 diagonal, so they were appearing the bosonic antifields, but in any case this is acting over something that is fermionic. And once again, HM is depending on something that is bosonic, but in any case, on it is acting something that is fermionic. So let's say that all the ingredients here are involved in some sense fermionic fields. So what is the difference exactly? So it's not too big. So the difference in KO dimensions, so between 1 and 7, is just telling us that D1 is anti-commuting with the real structure, while D2 is commuting. So this is our final result, but I have already said this from the beginning. So this is exactly what we were looking for. So this is a spectral triple such that the fermionic action given by this operator is exactly what we had before. So it was this BV action. So we have to impose this condition that are exactly the condition on the parity that we had from the initial model. But what I would like to underline is that this is not exactly a real spectral triple for the fact that it has a mixed KO dimension. So it has KO dimension 7 with respect to one part and 1 with respect to the other part. So let's just state all together the property that we have been seeing right now. So the structure of the BV spectral triple is giving some kind of geometric interpretation on some physical offset, let's say like this. So in the sense that, as I already said, the fields are appearing as components of the vector in the Hilbert space, in this Hilbert space. For what concerns the anti-fields, they're appearing as entries of the operator. And the parity of fields, anti-fields, ghost fields, and anti-ghost fields is determined by the commuting or anti-commuting of the Dirac operator with the real structure. And yeah, of course, also depending on another thing, because of course when we have an operator that depends on real variables, it preserves the parity, while when operator depending on Grossmannian variables, it changes the parity. So, but under this assumption, so this commuting or anti-commuting and this general rule, so the parity is completely determined by the spectral triple. And last, as I say, so if we consider the spectral triple with the operator as given by D1, this has KO dimension 1, or D2, we have KO dimension 7. So we can say that in some sense, the KO dimension is distinguishing between bosons and fermions. So these are the properties, but something more. So as I already said you before, once we have the extended theory, we have to carry on this gauge-fitting procedure. And a way to do this is just to keep enlarging our already extended theory by introducing these trivial pairs. So the point is that with this method, we can also take care of the trivial pairs, in the sense that also this part has been formulated in terms of non-commutative geometry via the introduction of this BV trivial spectral triple that appear like this. So once again, the Hilbert space is given by a direct sum, and we have a first term that is just a copy of M2C, which describe the auxiliary fields BI that are the one corresponding to the CI. And this second term is a copy of C2 that are the auxiliary fields determined by E. And once again, we have the fields inside the Hilbert space, while inside the operator are as entries the anti-fields corresponding. So it's really the same structure, and once again, we are forced to introduce a real structure. So as I said, also this triple is satisfied in all the same properties that were already satisfied by the BV spectral triple. And once again, the algebra is not giving us any information, so even worse this time. So the largest algebra that is satisfying the first order condition is just C. But okay, in any case, this is a trivial spectral triple in the sense that we are not. So the point is that we are forced to enlarge the construction, but we don't want to introduce any further information, so it's just technically that we need these extra fields. But let's arrive to the summary. So we started with a final spectral triple. We constructed this U2 matrix model that was just naturally defined by the spectral triple. We did this BV construction that allows us to define this BV theory, this extended configuration space with extended action. And we found a method, given this theory, to determine this real final spectral triple describing this situation. So what will be our next goal is to find this connection. So to try to give a method to go directly from this final spectral triple here to this real spectral triple describing the extended theory. So what is still need to be done? What for the future? So as I said, we want
avoiding BRST or
what? Sorry?
First, you want to avoid
No, not really. So what I want to do is to avoid to consider the Tate resolution and to apply all these algorithms. So Exactly. So I don't want to go from the setting of non-commutative geometry to something that is more inside, let's say, algebraic geometry, use order tool to arrive here, and then coming back. So I mean, the next step will be just find something really inside the world of non-commutative geometry to go directly from this finite spectral triple to this corresponding one. And so as I said, so this is picture could be extended because, I mean, considering here the trivial pairs and here the BV trivial spectral triple. So now we have all the ingredients that we need to carry on the gauge fixing procedure. So what about, let's say, a non-commutative geometric setting for this gauge fixing procedure? What does it mean in the setting of non-commutative geometry? And last, so what about the BRST cohomology in the setting of non-commutative geometry? There is a nice interpretation. I don't know. This is for the future. But for now, I just would like to thank all of you for the attention. Okay.
Can you do if you do the same procedure for quaternions instead of NCG, you run into troubles, or following it slowly, everything can just go smoothly?
Yeah, I don't know. So let's say that already to carry on the procedure for n bigger than 2 was already a point, because so the problem is at this level, so for this BV construction. So the point that is the construction of X tilde is based on the state resolution. So on really determine the relations between the partial derivative of the action. So the point is that we need to have an explicit description of S0 for a general theory. So, so we managed to go from 2 to n, but yeah, of course there are many.
Well, you take something away, so real quaternions are.
Yeah, but so it can be a direction to go. Yeah.
Can you call this one somehow for infinite spectral tables? The point is that if you do this line up for strings, well, fantastically famous. Probably 30 years, and you will get the number of citations more than any mathematician. So it makes sense to go with infinity.
Yeah, of course that is. Of course, it's a step, an interesting step to do. So let's say that in this context, so the point is that here this construction is really in the set of algebraic geometry. So then maybe once that this arrow is done, we can see what happened in infinite dimension. But of course, for infinite dimension, this part is definitely cannot be done in this way.
I can give you an advice. You don't have to do it for infinity. You do it for n arbitrary.
Okay.